Alright, so we're just going to start the chapter on t-tests. And we'll find, hopefully, that it's very similar to the hypothesis testing that we've done so far. The only issue is that, in general, I can't be sure what the population variance is. Up to this point, they just give me the population variance. Where do they find that? You're very rarely going to actually know what the variance is, and therefore what the standard deviation is. So we have to estimate the variance by way of our sample. And when we do that, it changes a little bit in my accuracy of my hypothesis test. Let me just see where is slide 7.1. So I'm going to refer back to this slide as we do the further steps, and the steps are the same as the hypothesis test steps we've seen before, and we'll just see the little differences as we go. So my example here is a study on the average number of hours that students study in a certain dorm versus the whole college or university. So it's found that for the whole college, the average number of hours studied is 17, but we don't know the standard deviation. We don't know the variance. We might say, oh yeah, it's a normal shape still, but we don't know exactly what the variance is. Then I look at my sample of 16 students in a specific dorm. They get an average of 21 hours. And by looking at the detail of each of those students, I can get the sum of the squares calculation on the way to calculating the variance for the sample. Sum of the squares is 694. So they just give it to me instead of looking at the individuals, so that I don't have to do it by hand. So then what am I trying to establish here? I'm trying to see if students in that dorm study more on average than the university average. So that will be population 1 versus the null hypothesis that they do not study more. So then my comparison distribution is, well, I'm going to have to move on first. Hold on, let me go to this one. So again, my sample is representative of the underlying distribution, regardless of what it may look like. I get a shape like this. If I take a sample of a decent size, then it resembles that distribution. If I get a distribution like that, it's going to resemble it. Flatter distribution, the sample is still going to be representative of the underlying distribution. So I'll use my sample to estimate the variance of the underlying distribution of population 2, because I'm assuming that between the two populations, population 1 and 2, the variance and the standard deviation will be the same. So if the sample has a very small standard deviation, then it's fair to assume, if it's representative, that my population will as well, and vice versa. Okay, so let me just see, 7.3. But when I estimate the variance, I have to make a little adjustment when I'm basing it just on a sample. If I know the whole population, that's what we did previously. But it can be showed with a little bit of math, actually a fair number of math, that I need to divide by the sample size minus 1. And we call that the degrees of freedom. n minus 1. To accurately estimate the population variance, it can be shown that I need an n minus 1 there. Otherwise, I'm just a little too high. Oh, too low, sorry, too low. So you can derive mathematically how this estimates the variance more accurately. If you use the n, you're just off a little bit from the population average. We call this an unbiased estimator, in that the expected value of this is the population variance. So that's the only thing we have to remember. That's the only thing, really. That I'm going to use my sample to approximate the population variance. And then I have to use an n minus 1 only there in the calculation. So if, for example, I have my different scores here, 5 different scores, same as before, we look at the deviation, we square that, get the sum of the squares, and now I'm simply going to calculate that divided by n minus 1, divided by 4 instead of 5. That's the only difference. Now it's a little bit perhaps hard to accept, because I don't explain why I need to do this, because it's just a little bit too mathy for us. Too mathy to show that using an n minus 1 is more accurate to estimate the population variance. Okay, so let me see, example 7.4 would then here show my hour study example. I have 16 people. I get the sum of the squares value of 694. That I'll divide by n minus 1, my degrees of freedom, which would be 15, and I can get an estimated population variance of 46.27. So let's go back to slide 7. Whoa, it's too much. I got a little bit excited. All right, so now I have to have the variance and the standard deviation to be able to look at my distribution of means. They didn't give it to me. I don't know the population variance, so I'm estimating it by way of my sample, and I'll get my 46.72 that I'll use. So now I'll use that as if it's the population standard deviation. So my distribution of means will still be the same mean of 17 for the original population, the university-wide population 2. My standard error I'll now denote as S instead of sigma to indicate that it's an approximation. If it's the population parameter, then I'll use the Greek letter sigma. If I'm approximating it by way of the sample, then I'll use an S. But it's still the population estimate here. Where is my standard deviation? Divided by root n. Or you can take the variance divided by n, just as before, and I'll get my estimated standard error of the mean as 1.7. So nothing's really changed, except that I had to go and guess at the population variance. Everything is the same outside of that. Now the difference is that I can't use a normal distribution in exactly the same way. So when I'm estimating the population variance, I lose some accuracy. The way to compensate for that is to use something that looks like the normal curve, but the tails are a little bigger. So I'm a little bit more conservative. So let's look at what that is. So we call that a t-distribution. And yes, it has a mathematical function formula behind it, which is extremely unpleasant to look at. But you're welcome to search for it. We're hiding all of that to not freak us out a little bit. So it depends on how big my sample is. If I have a very small sample, then it's fair to guess that my approximation is not going to be that accurate. So I want to have a bigger tail here, so that in my hypothesis test, I'm going to have to be more extreme before I make a decision. Bigger tail for a small sample size. Sample size -1 is the degrees of freedom. So for a very small sample size, I have a nice big tail to sort of compensate for the possible mistake I could have made by estimating the variance. If my sample size goes up, the degrees of freedom go up, and the higher that is, the closer I'll get to the normal distribution. So there are actually many different t-distributions, depending on the sample size, depending on the degrees of freedom. But they eventually, the higher the degrees of freedom, the closer I'll get to a normal curve, because the bigger my sample, the more accurate my estimate is for the variance. And I don't have to compensate for that too much in the tail. So I have a slightly different distribution, the t-distribution. Very similar in terms of my understanding. It has a similar shape. I'm using it exactly the same way, but the t-distribution will have a different table that depends on the degrees of freedom as well as my cutoff and the alpha value. So that was 5. So for the table, it would look a little different in that I now have this degrees of freedom property as well. And technically I have a whole bunch of table values for each of these. So to avoid the messiness of that, they just give me some common alpha values. 10%, 5%, and 1%. So if I'm looking at 5% in the tail, this is for the one-tail test, either left or right, it's the same because of symmetry. Or I would have a two-tail test where the 5% is split up into 2 little pieces. And then I just have to look according to my degrees of freedom, which in this case I have a sample of 16, so the degrees of freedom is 1 less, 15. And under 5%, if I'm looking for an alpha of 0.5, then my cutoff value, which I'll call a t-score now instead of a z-score, t-score is 1.753. So everything works very similar, very similar. But because I had to estimate the variance, I need a slightly different distribution to compensate for the possible error, and I have a slightly different cutoff value. Everyone with me so far? It's not really different, so there's no need to panic. It's not different at all. I just have a different table, and the distribution looks very similar, so that makes me feel better. Let's go back to 7.1. So that was step 2, where instead of the normal distribution, I'm now going to use a t-distribution that depends on the degrees of freedom. So just remember, the degrees of freedom is 1 less than the sample size. So there's no formula for that. That's what you have to remember. 1 less than the sample size. So now everything's going to work the same way as before. Let's have a little sketch here to visualize what's happening. That's sort of balanced. So now I have a t-distribution. The degrees of freedom is 15, because that's 1 less than my sample size of 16. I'm deciding on an alpha of 5%, or 0.05. And I looked it up. What are we looking at here? Well, my hypothesis, my research hypothesis is trying to see if the average number of hours is more than the university-wide average. So my cutoff is going to be here at a t-score of 1.753. 3. I don't know how extreme that is. It's something on the right. So I have a right-tailed test, so that this is 5%. That's my alpha, the probability of making a type 1 error. Then I'm going to look at my sample. What does my sample give me? My sample gives me average number of hours in the dorm is 21. So convert that to a t-score with the same way, the mean minus the population. Well, this should really be a mu m, because I'm using the distribution of means. This is still a distribution of means. So mu m is just the same as the population. And my standard error of the mean is now approximated from my sample. So I take the difference, divide by 1.7, and I get a 2.35. Oh, that's out there, isn't it? Let's go with purple. So I get a 2.35, just to exaggerate it, I'll put it over here. 2.35, let's say observed. By way of my sample, I'm observing something much more extreme. So what do I conclude? That I reject the null hypothesis in favor of the research hypothesis. So everything works in pretty much exactly the same way, except if I don't know the population standard deviation or variance, I have to approximate that by way of my sample. That puts me with a t-distribution, but everything else is the same. Yes?
Did you know the mean or the mu of the distribution because it told you so?
Yes.
Or, oh, okay.
It gave us the mean of 17.
Right. And we're assuming that.
So I have to know something of the distribution. Well, for our purposes, to make it simpler, I have to. This is the situation where the variance is unknown.
Right.
And the mean is, yeah. The mean is something easier to estimate than the variance. The variance, yeah, if I don't look at the whole population, I'm always going to be a little off, whereas with the mean, it's just an average. It's easier to estimate, and easier to find as well. So, just to go a little bit more general, if I have one of the two, I have the mean and not the standard deviation, then how does it change? Luckily, it doesn't change that much. But in another situation, you might not know the mean either yet. Then we're in another situation as well. So just one change at a time, working towards more and more realistic, perhaps, distributions and tests. So the distribution changes a little bit, but the idea of the hypothesis test steps are all the same. It's all the same. And I can calculate power and all those things in exactly the same way. It's nice that this shape resembles the normal shape, so everything just feels the same, which it is. So I'll reject the null hypothesis in favor of the research hypothesis. It's a significant enough observation at the 5% level. Any other questions on that? So when I look at this, it shouldn't be really strange. That's why I wanted to just get this first part out of the way before we look at t-tests in general. Let's see, I have another example. Where were we now? Hours studied, using my t-table, 7.8. So we've done that. That is just another representation of what we did here. I have my population. The comparison distribution behaves the same, pretty much, as what we've had before. It's now just the t-distribution with a slight safety adjustment to compensate for my variance estimation. But everything's used the same. I have my cutoff. Then I find my sample. Where does that put me? It's more extreme. Then reject the null hypothesis. Any questions on that? I need the big picture first before worrying about the detail. Big picture, big picture. So the last example is looking at a class like ours to determine if people in the class, in a psychology statistics class, responds differently to the question, are you a morning person? Then the average rating of 4. So I look at the population of people in the class versus the population of everyone else that has an average of 4. And I'm trying to see, is our class different from the population in general? Now I know that on average people rate on this question with a 4, whatever the scale may be. And I just want to see if it's different from a 4. Is our class different from that population-wide average of 4? So I don't know the variance again. I have no idea how much variability there is around that average of 4. So I'll take a sample of 105 students, much bigger class than this one. 105 students, and they give their ratings to the question, and I get some of the squares, or I get an average of 3.46, a little below. Not sure how significant that is yet. I have the sum of the squares, and the degrees of freedom is 1 less than the sample size, so it's 104 that I divide by to get a variance estimation, sample variance of 3.1. So now let's see, what is the distribution of means? That's the same as my population mean of 4. I get the standard error with from my approximation, my sample variance of 0.17, and I have a t-distribution with degrees of freedom 104. Let me just see if there is a sketch here. No, there isn't. Let's make a sketch. So I think to some degree how well I understand this, or how easy I find this bit, is sort of confirmation of how well I understood the basic hypothesis testing procedure, because it's pretty much the same. So, what am I now? I want a 5% two-tailed test. So I'm going to have, I don't know if the average rating, if we're more or less a morning person, morning people, I suppose, for our class. So I want 2.5% here and 2.5% there, just to cover either side. I'm not sure if it's going to be more or less. So then with a degree of freedom 104, I can look it up in my table, which we'll do in the additional examples and the quizzes, and I'll find that I need a t-value, a t-score of 1.984 plus or minus 984. Now I look at my sample mean, 3.46, convert that to a t-score to see where does this sit in the distribution of means. It's a t-distribution, degrees of freedom 104. So I calculate that, 3.46, compared to the distribution mean, standard deviation estimate, and I get negative 3.18. Ooh, that's out there. Let's put it over here. So I'm observing negative 3.18. So I can again say that it's significant enough to reject the null hypothesis in support of the research hypothesis that the means are actually significantly different. And more so that a class like that is less than the average rating for morning people. Morning person, yes or no. Does the process for this hypothesis test procedure make sense? It's exactly the same, just a slightly different distribution because we had to estimate the variance. Okay, so this is just a summary of the steps. I restate the question as the research and null hypothesis. That's no difference than before. Population means no difference. Population variance, I just have to estimate from the sample. No difference in the method for calculating anything else. I just have to use degrees of freedom and my t-table. And there's just a summary of the different things we need to be able to calculate. The sum of the squares divided by n minus 1, and then everything else is the same using that. So it shouldn't be strange or different to answer questions where I don't know the variance. It's just a little adjustment. Everything else is exactly the same. Any questions on the basic t-test? All right, so we've done the basic t-test, where it's very similar to the one using a normal curve, except I don't know the standard deviation, I don't know the variance. So when I have to approximate the variance by way of a sample, then I shift to a t-distribution that allows for a little bit of safety in the tail. A thicker tail, but still the normal curve shape, so I can visualize it in the same way, and the hypothesis test steps are the same as well. So we're going to do two more types of tests, of t-tests. The first one is where I'm testing what we call dependent means. So in general, I think of a group of people before a certain treatment is administered. Then I look at them before the treatment and after the treatment, and I see if the average rating of whatever the treatment is trying to affect has changed. So if I'm treating stress, for example, I survey the people before the treatment, after the treatment, and see if there's a difference in the average stress rating. Now, because the people are the same in both situations, they're dependent on each other. The means depend on each other in some way. It's not completely separate, it's the same group of people. So in this first, so we also call that repeated measures design, where I'm repeating the same group, measuring them again before and after the treatment, or within subjects design, when the same people are tested twice, before and after some sort of procedure. And I'm trying to see if the procedure, if the treatment had a significant effect. Like medication, or an exercise routine, or what people do before, after leaving home, things like that. So I see it as some sort of treatment. So for that, I need to look at what we call difference scores, and look at how the differences among all the individuals are distributed, and what happens to the average difference. So in this first example, I'm looking at a sample, it's a smaller sample, or smaller little bit of a research paper that has been done, looking at people's effectiveness in communication before and after marriage with basic marriage counseling as they're preparing to get married. And this sample only refers to a sample of 19 men to see how their communication quality has changed before and after marriage. So they've gone through some basic counseling, but nothing major, seeing if there's an effect due to that basic premarital counseling. So I have my 19 men here. They were rated on communication quality before getting married and then after the process. And I want to look at the difference, the after score, regardless if it's more or less, after minus before. So some of the people will have a negative difference, meaning that their communication quality actually dropped. Some of them stayed the same, so a zero difference would indicate staying the same. Individual E, his difference increased, meaning that the after rating is higher than the before rating. So I get positive, negative, and zero values for the difference scores. Everyone happy with the idea of the difference? I think it's an overly complicated concept. It can be positive, negative, zero meaning no change. So I now want to look at the difference scores and compare my sample of difference scores to the distribution of all possible difference scores that I could get. So my comparison distribution that I'm going to use for my test is going to come from the difference scores, so that I can sort of combine the before and after. And when I look at the distribution of difference scores, I'm trying to see, is the mean from my sample, does that suggest a mean that's not zero, meaning that there has been a change in the difference for my population? Now, of course, I only have a sample suggesting what the population, what has happened to the population due to this process. So my sample is being used to make a conclusion through hypothesis testing about if this marriage process affects the communication of males in general going through this process. Any questions so far? So I'm trying to see throughout the similarities between this and what we've seen before. Hopefully, by way of exercises, we've gotten fairly comfortable with the t-test, the basic t-test. It's really very similar, except if I now want to test change before and after, I'm combining it as a difference score, and those are now my sample values. And I'm trying to see if the mean, the sample mean of difference scores, if that is significantly different from zero. Because zero would indicate there's no change. I'm trying to see, is it different and is it significantly different? To conclude that there is a change in the before and after for the whole population. Alright, so that's the only adjustment for this type of test. Test of dependent means, looking at the difference scores instead. So my research hypothesis is what I'm ideally hoping for. That's how I see it intuitively. What I'm ideally hoping for is that there is a change. Now I don't necessarily know if it's a positive or a negative change. So I could use a one-tailed test or a two-tailed test by way of hypothesis testing. So the research hypothesis is going to be that there is a change in the means, or in the difference. Yes?
So you're looking to see if there's a change from, like, which mean?
So now everything's going to be different scores.
But
And I'm looking at the distribution of all different scores. And I'm looking at my sample average of the differences, and see where that sits in the distribution. Is it extreme enough to suggest that the population mean of differences is not zero, meaning that there is a change before and after. So everything is differences. So I really only have one set of sample values, mixing the before and after as differences, so I only have one set to look at.
and then you're comparing them to the mean of
All differences.
also of themselves.
So these are just 19 males.
Yeah.
If I look at the population of all possible males that go through this process, all possible differences,
Yeah.
that has a distribution as well that we'll assume to be normal because it will come from two normal distributions,
Yeah.
but I have to use that as my comparison distribution. Everything's now in terms of differences. That makes sense?
I think so.
Sort of.
Yeah. Very close to yes.
Very close to yes. So under the null hypothesis, so the research hypothesis is what I'm hoping for, that there is a difference, so that the mean population difference is not zero. And my null hypothesis is that it is zero, that there's no change. So then I'm going to look at my sample. My sample is going to give me an average difference. It's probably not zero, but I need to see if that's significant enough.
Okay, yeah.
Chances are I'm not going to get a zero from a little sample like this. But where does that fit in the distribution of all possible differences? Is it common? Do I get something that's significant? See where it fits. So everything's the same in terms of the hypothesis test way of thinking. I'm just looking at differences instead. So it's a little adjustment. It's a little adjustment. So the research hypothesis that there is a change, there is some difference, and the null hypothesis that there isn't. So the computation is exactly the same as a t-test, except that I have to convert everything to differences. And usually, for our case, I can't really think of an example that will have that's not the case. We are looking at whether it's different, period. Meaning, by comparing it to a population 2 with a zero difference, meaning there's no change. So there either is a change that's significant or there's no change. All right, so let's go to the first slide now, where I'm starting my hypothesis testing process. And remember that this is just a guide. Some don't want to religiously follow these steps. It's a guide through the hypothesis testing procedure that you're welcome to follow, but there is some flexibility in terms of which things you write first. So my population 1 will be husbands who receive the counseling through the process of getting married. Population 2, husbands whose communication quality does not change from before. And I'm trying to see if I take a sample of my population 1, all husbands who receive the counseling, is there a change? Is there a difference that's significantly not zero? So my research hypothesis that the populations are different, now mu2 I can see as a zero. I'm testing it against no change. But in general, there are probably some situations where it might not be, so we're leaving this as general. But for our examples, I'm comparing the mean of population 1 against a 0, meaning no change. So the null hypothesis is that they're the same, that there's no change. So then I'm going to look at the comparison distribution, which is going to be distribution of all possible differences. That's going to have, under the null hypothesis, that's going to have a 0 mean, meaning no difference, but I don't know the standard deviation. So I'm going to estimate the variance again. Let's look at the calculation. So here are all my samples, 19 of them. I look at all the difference scores. Those are the scores I'm focusing on. To get the variance, I need to look at the deviation. Well, I have to look at the average. And I get the mean to be. It's a little low, but I want to keep everything on the screen. Add all the differences up, divide by 19, and I get negative 12.05. That's the average difference. So on average, the communication went down a little bit. Then I look at the deviation, the difference between the scores and the mean. So this difference, for example, the first one will be negative 11 minus negative 12. So it's plus 12.05, giving me a 1.05. And I do that for all of them. Only 9. Is that actually 19? No. Maybe they're listed all of them. Then I square the deviation and look at the sum of the squares, same as way back in the beginning. And I divide by the degrees of freedom, which is 1 less than the sample size, because I'm trying to approximate the variance of the population. So, under the null hypothesis, the mean is 0. Take the sum of the squares divided by n minus 1, which is called the degrees of freedom. I get that, divide, so now I'm looking at again, the distribution of means. So it's the distribution of means of the difference scores. Because I have an average difference score from a sample that's bigger than 1, whenever my sample is bigger than 1, I have to look at the distribution of means. All of those things are still the same. So I divide by n, take the square root to get the standard deviation as, or the approximate standard deviation as 2.84. Same as before, except I'm looking at differences instead. Everything else is the same. Everything else is the same. So now we're going to step 2 is now summarized here. So I'm estimating the distribution of means of difference scores. 0 under the null hypothesis, no change. Standard deviation 2.84. And because I've approximated the variance or standard deviation, I'm going to use a t-distribution. Degrees of freedom is 1 less than the sample size. So now everything is the same. Let me just check, do I have a sketch here? Do. So my population, that's not accurate, the numbers are not right, so don't look at the numbers, just the idea. I have a normal distribution of all the different scores. I look at my comparison distribution, which is the distribution of means, again, because my sample is bigger than 1. So I need to see where does the average difference for a sample of 19 people, how does that compare against all possible sample means that I could get. And then I look at my specific sample and see where that sits. Now those numbers might not be correct, just want the picture. So let's go back here and make a little graph ourselves to visualize what's happening. So I have my t-distribution. Just the visualization doesn't have to be perfect, although that's not bad. The more I do it, the better it gets. That's a little off, but still. So looking at step 2, I have everything here. I have, that's a 0. I have my standard deviation as 2.84. Everything's the same as before. I want to see the similarities. Focus on the similarities. And there's really only one thing that's different, which is I looked at the difference scores. Everything else has been the same so far. Then I have my degrees of freedom, but that's n, I guess I could write it here. N minus 1, which is going to be 18. That's what I'll need to look up in my table, my T table. So then I'm just deciding on an alpha of 5. But I don't know if the differences will be more or less. I'm just looking for something that's different than 0. So I have a two-tailed test. So I like to visualize here, 2.5%, 2.5% for an alpha of, you can write 5% or 0.05, doesn't matter. So then I go to my table and I look up what is the t-score that gives me that cutoff. Let's do that. Good practice, why not? My t-table I have to find on page 677. 677. They don't give me the whole table. They just give me some common values. I'm looking at a two-tailed test. So the right side, the middle column, two-tailed test for 0.05. Degrees of freedom is 18, and I get 2.101, which is what they get as well. So this is 2.101. That's T. Negative 2.101. The t-score. Everyone with me so far? See the similarities. See the similarities. And if you're sort of up to speed, then this shouldn't be too bad. And if it is a little confusing, then that should tell you that you need to go back and build it up correctly. I don't want to jump over anything because it builds up systematically and in a specific way to help us. So now I look at my specific average, my sample said the average differences that I got was negative 12.05 from my sample. It seems like a lot, but depending on the standard deviation, I can't say for sure if it's significant. In this case, so I calculate the corresponding t-score from that, from the mean. That should really be a mu m, because my distribution is the distribution of means, but it's the same as the population. And my standard deviation, and I get a negative 4.24, which I'll do in purple. That puts me, I'll just extend it so I have space. Doesn't have to be to scale here or anything, as long as I have the positioning right. That puts me over here. Let's say here observed, negative, let's say 4.24. So what do we conclude? It's extreme enough past the left cutoff that I can reject the null hypothesis at this significance level, probably a little more. If I was doing it in Excel, it would give me the best significance level I could, not Excel, SPSS. It would give me the best significance level I could have chosen. So I do have a little bit of space. And I also know that the differences are extreme on the left. What does that tell me? So the differences are significantly negative. If I go after minus before, there's negative change. Meaning, what happens to men going through the marriage process? They get worse. I know. Isn't that typical? They get worse. I don't even think you need a test for that, yes. Experience will tell you yes. That does sound right. So we reject, based on this sample, we can say we reject the null hypothesis. We have evidence that supports the research hypothesis that there is a difference. everything's the same except I'm looking at differences to establish if there's a change before to after the treatment. Any questions on that? Does it make sense?
I was just wondering, so in this case, we were using differences, but would you also use T-scores for surveys or samples that didn't include differences?
So here I'm doing the difference because I'm testing to see if there's a change due to the treatment. So I'm comparing two things. I'm comparing a before and an after. But my t-test so far previously had a single sample value.
Yeah.
So I need to sort of merge that so that I can use what I've done before.
Okay.
That makes sense?
Yeah.
Yes, I'm trying to relate it back to what I know. And what I've done previously was just test a single score, a sample of single scores. Now how can I have these two things merged into one to be able to use what I've done before? When I'm only interested in the difference. Is there a significant difference? So I look at all the differences and look at that as my score instead. So that's really the only difference. Yes.
The thing I don't get about research hypothesis is even if the score was before where we have our cutoff, like let's say it was just slightly before that,
Here?
yeah, isn't that still showing that there's a difference?
Yes. But it's not significant enough.
Okay.
Meaning, so the alpha, remember, was my type 1 error.
Yes.
What was the type 1 error? Anyone
You
remember?
reject the null hypothesis. The null hypothesis is true.
If I reject the null hypothesis, but it's actually true. So I don't want that to be too big. So I don't want to reject it too early, because then I run the risk of, if I get something over here, according to this distribution, those values could have come just because of natural random fluctuations.
Yeah, okay.
So if I get a sample from 19 men, and I get something over here, that could have happened even if the null hypothesis is true.
Okay.
Just because of natural fluctuations. I'll never get anything perfect. There's
Oh,
always
sure.
variation.
Okay.
So if I get a sample that's common, I don't want to be too quick to make a decision on that, because it doesn't necessarily mean that there's been a change.
Okay.
These values are common. So what do I decide? Where is the line between common and not common? I decide beforehand,
Yeah.
5%. Here's my line. Anything before that, and I'm going to see that as fairly common, that I can't necessarily say it's because of the change. But if I get something very extreme, it's so unlikely that I'm thinking there has been a change so that these values now become more common, and I'll observe them. And the only way that I'll observe these as more common values is if there has been a change in the population. There's been a shift to a negative difference, making these more common.
Okay.
And that's why I'm observing them.
Yeah.
So I never know for sure. There's always a little chance that I'm making a mistake. But I want to hopefully have that chance of making a mistake sort of kept to a minimum. But you never know for sure.
Okay.
You could have decided, no, I'm happy with the 10% cutoff. And then you'll reject the null hypothesis earlier if you see these as not common either. And you might be right.
Yeah.
You might not.
Okay. Thank you.
Some people say, no, 5%, that's still too quick. This is not extreme enough. Let's go 1%. So then I'm not going to reject it unless I really get something out there, which this would still be.
Yeah.
There's no, the chances of getting something like this is so small that it's safer to assume that there has been a shift making these more common. So if I get something like this, it suggests that there has been a change. The difference, the population difference, the average population difference is not 0 anymore. There is a change. So the idea, if I can be comfortable with the idea of hypothesis testing, then these things are okay. Any other questions? Big picture helps a lot. All right, so that was that example. 12, 11, 13 is just a little graph, ignore the numbers, just to sort of see a population. Smaller variance when I look at the distribution of means, which I have to because my sample is more than one value. Look at my specific sample, where does that put me? In this little example, it puts me to the right. In this one, it puts me on the left. Okay, let's do one more. So a class is surveyed, and they're asked 2 questions. Rate the closeness to your mother and the closeness to your father. And so the same people are being rated, and I'm trying to see if the closeness rating is the same. So let me just see if I have a table. I do. So I have 2 ratings per person. So this is quite the same as a before and after, but I can see it as the same because they're still dependent on each other. This person's 2 scores for mother and father aren't unrelated. There's a relationship between those scores. They're linked in some way. And I'm trying to see if there is a significant difference between the closeness to your mother and to your father based on this sample. So I'm again going to look at a difference, and it doesn't matter which one I pick first. For example, I just make a decision, mother minus father. So I get differences to just measure if the average difference from my sample suggests a population average difference that's not 0, meaning that they're not rated the same. So I'm going to look at the average. Where do I calculate average? Let's see. I'll add up all the different scores and divide by how many there are to get my sample mean. Oh, it's right there. 1.44. And then I also have to approximate the variance in the same way, calculate the deviations, square them, sum of the squares, divided by n minus 1, and then convert that to my sample standard deviation, or my standard deviation approximation for the population, which will then be a t-distribution because I had to approximate the variance. So my research hypothesis is again going to be that there is a difference, and the null hypothesis is that there is no difference in the population. So my mean for the population as well as the distribution of means would be 0. And my approximation for the standard deviation is 0.23, and I have a t-distribution with 108 degrees of freedom. Let me just check if I have a sketch. I do not. Okay. So let's make our own sketch. It helps me a lot to visualize what's happening here. Even though it's very similar to what we've done, repetition helps me remember. So before we get, let's do it right now. Helps me remember as well as practice my nice sort of class group. So I'm going to look at I have a sample that's more than 1, so I have to look at the distribution of means of different scores, and I've approximated the standard deviation. Under the null hypothesis, I'm going to see if it's significantly different from a 0 population mean, and my standard deviation I just said 0.23. So I'll specify here T distribution, degrees of freedom should be one less than the sample size, which is 108. So that's the what I call the comparison distribution, however many calculations you need here. So because we're doing these things by hand, it's a little tedious to do that step 2 to get this guy. A little tedious. But often we're given a shortcut by being given the sum of the squares. We can be given the 616.86. So you don't have to fill in the table. You're given these bottom values, and then it's not so bad. So I won't necessarily expect you to do all the individual calculations. I'll give you the sum of the squares and all these numbers. So you just have to do these bottom steps. So it's not so bad. So then let's suppose in this case we want an alpha of 1%. So again, I'm just looking if it's different or not. I don't really have anything to suspect one's more than the other. And I don't want to run the risk of assuming that. So I just want to see if it's different or not. So with 108 degrees of freedom, let's look at my table. What is my cutoff? Let me visualize the cutoff first. So yeah, it's probably a little more extreme than I'm making it, but it doesn't really matter. It's all just to position it. So I'm going to look at my table. For 1% two-tailed, go down degrees of freedom, it stops at 100. And then it's so close to the normal distribution that I can just take those values. 2.576. Is that what they have? Or was that to check? That's not what they have.
They chose the number that's in line with 100.
Oh. Well, I don't know if I agree with that. But, so the slide makes sense, okay. If it's more than 100, I would pick the other one.
How did you get the 2 point?
So they go up to 100, and then anything bigger than 100, I use the bottom value.
Oh, I see.
So maybe they argue it's not big enough past 100, but I don't know, decide. I would use the bottom one. But so that the slides make sense, which one do you want to use? Stick to the slides or do what we want? 108 is more than 100, so I picked the bottom one. But you'll see it doesn't actually matter. Our value should be hopefully extreme enough. Or not extreme enough. Which one do you want to do?
Let's do the
On the test, what should we do?
On the test, I would pick, if it's more than 100, I would go to the bottom one. So, let's pick 2.576.
What if DF was 101? What would you want?
I guess then you can argue both. I mean, this is really, it does continue. The
Just
table
100?
does extend, just not in our book. So, you could argue, should I risk using a limited table, or should I look it up online and see exactly what it is past
Oh,
100?
okay.
So if I'm actually doing the study, then I would not be restricted by my textbook table.
Yeah,
Look online, what is 101, what is 108, exactly.
okay.
So we're a little limited, so we can argue both. But if you start saying, oh, 108 is close to 100, well, where is it not close? So I think for our purposes, using the textbook, the rule should be 100, past 100, and I use the bottom one. But the table is bigger than this, of course. That's just the summarized version. So I prefer to use this one. But honestly, if I see you've chosen the 100 instead of the infinity one, you know what you're doing. I won't be that cruel and subtract marks like that. So I'll accept both in this case, to be fair. All right, so now I'm looking to reject if it's in here, 2.5% and 2.5%. Let's see what our sample is telling me. So now I look at my sample and I get an average of 1.44 for the difference between mother and father. So in my sample, mother closeness is a little higher. Don't know if it's significant. So I find the corresponding t-score and I see it's a 6.26, so it really doesn't matter what you pick, to be honest. Get something out here that is significant enough, 6.26. So regardless of your limited table, you can safely, according to this alpha, safely reject the null hypothesis. I have evidence that supports that there is a significant difference that supports the research hypothesis. So it didn't really matter which one. In our examples, they make it so it's not that close. If you pick the t-value that's a little different, it's still extreme enough to not affect my ultimate conclusion. Any questions on that? A couple of examples and you see it's very similar. You just get used to the little differences as we go. We make little differences from one step to the next. That was this example. Okay, so let's, just before we take a break, talk about effect size and power. Now, it's good news and bad news. Actually, I think it's all good news. When I talk about effect size and power, it works in the same way as our power calculations using the normal distribution, except that I don't have a t-table as complete as the normal one. Because for every degree of freedom, I have something similar to all these z-scores that I had before. So it's not practical to, in this textbook, list three, how many tables? 1, 2, 3, 4, for each degree of freedom. So we don't have all the information in our t-table to do the power calculation by hand. So we can use a table like this for effect size and power to get an estimate of the power. It's not going to be exact because there are little jumps here, but it does give you an idea. If you had the complete t-table, you could have done the same calculation. So we're only going to do the power calculation for that basic case that we've done before. For these, we just look it up according to these tables, which are some values that have been calculated for us. So let me just write down, before we talk about power, the effect size is going to be very similar to what we've seen before. Effect size is simply going to be D, mu1 minus mu2 over sigma, for my approximation of it. Now, in our case, for most of our examples, mu2 will be 0. We're comparing against the null hypothesis, which had no difference. So just remember that this is for the population of differences, not the distribution of means. If you go back to our previous one, it was the population parameter here, not the distribution. I want to see in my population of differences, how far is the difference that I get? How far is that actually? What is the effect of the treatment? All right. So for example, let's do an example. if the average difference is 6 and the estimated population standard deviation is 12, then D is 6 over 12, or 0.5. And I have the same sort of classification for effect size: small, medium, large, 0.2, or roughly 0.2, 0.5, and 0.8 and above to be considered large. So when I want to calculate the power, then I simply need to know what is my sample size. Remember, power was affected by sample size as well as effect size. So I would have the effect size and the sample for the two different kinds of tests. Our examples had a two-tailed test. That puts me somewhere close to some of these values, and I can have an estimate of how much power I have in my study, and therefore what is the probability of making a type 2 error. It's just 100% minus the percentage here, or 1 minus its probability. So I just sort of look for the one that's closest, and for some of these you'll see if my sample size is big, then many of these just are close to 1, meaning I have a very small chance of making a type 2 error. There's also another table that does the reverse for you. If you're looking for sort of the standard power of 80%, what is the sample size that I'll need to get? From maybe an initial study, you can get an estimation of the effect size by looking at the mean that you get and seeing how different is that from 0. So you sort of have an estimate: is it small, medium, large? And to get a power of 80%, how many sample values do I need? So if I have a big, large effect size, I don't need that many sample values to avoid a type 2 error, because my observation is so significant. If I get only a small little difference from 0, excuse me, then to avoid a type 2 error, I really need to have a larger sample size to get that distribution of means nice and thin, so it overlaps with very little, so that the probability of a type 2 error is kept to a minimum. So I use these tables, and we'll use these in the quiz and the additional examples, but it's fairly straightforward when we don't have to calculate it. We only calculate that initial basic one, because we don't have enough information for the t-table in our textbook. All right, so just to summarize, when I have the t-test for dependent means, what is really different from what I've seen before, from a one-sample t-test? I have my research hypothesis and null hypothesis, very similar. I'm looking for difference or no difference. Comparison distribution is still the distribution of means. Distribution of means with a population mean under the null hypothesis of 0. Then I have to look at the differences. That's the only issue. Still approximate the variance and standard deviation. And everything else is the same. Determine the cutoff sample by way of my t-value. See what my sample suggests as a t-value, and decide whether I reject the null hypothesis or not. Everything's the same except I'm looking at the differences. So it's really not so bad. Any questions before we take a break?
I was wondering, the estimated population standard deviation, is that the same as saying
The same as this one that I get from here.
But is it, okay, so
For
this...
the population, not for the means.
No, I was just wondering this estimated population standard deviation is the same as the degree of freedom? Like, does it mean the same thing?
No. If I look at this, I get this is the variance, where I take the sum of the squares and divide by n minus 1. And then the square root of that is my population standard deviation.
Oh.
So I'm taking the sample and dividing by n minus 1 to get the variance. If we look at our example, let's go to the first one, it's a little nicer. That was the husband one. I looked at my square deviations from my sample, different scores, and I calculated, and I approximated the variance by taking the sum of the squares, dividing by n minus 1, when I'm approximating the population,
Oh,
instead of n. And then I just take the square root of that, which they don't like to do for some reason. Take the square root of that to get, it's not showing here, to get the standard deviation. It's shown up here somewhere.
Oh, so it's the.
There it is, 2.84. No, that's not enough. They don't like to do it. You just take the square root of that to estimate the population standard deviation.
Okay, so the degrees of freedom is just something you use in order to
In the
get
calculation,
Oh,
yes. Instead of an n, use an n minus 1 to be what they call an unbiased estimation.
okay.
Let's just say an accurate estimation of the variance.